In this lecture, we will learn about cosets and quotient group. So, let us consider a group, let us say this is the group G, and suppose this is a subgroup H. Okay. So, let us define what are known as the cosets of G with respect to H. Okay. So, consider all the elements of the form AH. Okay. So, AH is defined as all those G belonging to G such that G is equal to A times H for H belonging to capital H. Okay. So, this is our set H, and we are going to multiply all the elements in H by A, what we get, and once we do that we will get another set which we will call as AH. Okay. And this is going to be called as a coset. In particular, this is a left coset because we are multiplying on the left. Okay. So, now if you take an arbitrary group and construct all its left cosets, we will get different cosets. Let us call them as A1H, A2H and so on. And this collection of cosets is going to, if you take the union of them, that is going to be the complete collection. In other words, union over all A belonging to G AH will be equal to the set G. But what is more interesting is, if you take two cosets, they either are one and the same or they are disjoint. Okay. So, this is the claim. The cosets partition G. Okay. So, if you have, so what this means is, suppose AH and BH are cosets, then either AH is equal to BH or AH intersection BH is equal to empty. Okay. How do we prove this? Okay. And if we have this claim, it is easy to see that if you take all the cosets, that will and take the union of that, you will get the entire set, because if you look at H, H is a subgroup. In particular, the identity belongs to H. Okay. And if we take G times E for any arbitrary G belonging to the group, you are going to generate the element G. So, if you consider the coset GH, that contains G. Okay. So, the union of GH over all G will certainly exhaust the complete collection of groups. Why is it true that it is either empty or two cosets are the same? So, let us assume that the cosets have some non-trivial intersection. If they did not have any intersection, then we are fine, because that is the condition AH intersection BH is empty. So, suppose let us say alpha belongs to AH intersection BH. Okay. So, that would mean that alpha is equal to AH1, or exists an H1, an element H1 such that alpha is equal to AH1 and alpha is equal to BH2. Okay. And therefore, we can say that AH1 is equal to BH2. So, AH1 is equal to BH2, therefore, A is equal to BH2 H1 inverse, and since H2 and H1 are members of a group, we can say that this was a subgroup. So, H2 times H1 inverse will be equal to BH3 for some H3 belonging to H. Okay. Let K is equal to AH be an arbitrary element of AH. We want to show that K will belong to BH, and an exactly same reasoning will show that any element in BH will also belong to H. So, let us first do the proof that any element of AH will belong to the set BH. Okay. So, K is equal to AH. So, A can be written as B times H3. So, K is equal to AH can be written as B times H3 times H, and that is equal to B times H4. Okay. So, this means that K must belong to BH. Okay. So, we took an arbitrary element of AH and showed that it belongs to BH if there is an intersection between AH and BH, and similarly you can show that any arbitrary element of BH must belong to AH if there was a common element. So, that concludes the proof that the cosets are either disjoint or they have a they are one and the same. Okay. So, now this will help us prove the following theorem known as Lagrange theorem. So, let G be a finite group and let H be a subgroup of G. So, clearly H will also be a finite group, then order of H divides order of G. Okay. Why is this true? Okay. If you consider, so all that one has to do is consider cosets of G with respect to H. Okay. So, order of H is the number of elements in H and order of G is the number of elements in G. So, if you consider the cosets with respect to H, they are going to be, let us say A1H, A2H and AKH. Okay. So, let us say these are the distinct cosets. Okay. Some of these, I mean, if we had taken all the elements of G, some of the cosets may overlap, but here we are just enumerating the distinct cosets. Let us say k of them are there, which we call as A1H, A2H and AKH. Okay. And these cosets, these collections partition the collection G. Okay. So, their sizes if you add up, we will get G. So, size A1H plus size A2H plus size AKH is equal to size of G. But note that every coset is of identical size. Size AIH is equal to size AJH. Okay. Why is this so? This is equal to the size of H. Okay. Now, if we assume this fact, what we can show is, what we can immediately conclude is that the total sum on the left hand side is equal to k into size of H, and that is equal to the RHS, which is the size of G. So, this would be the proof, but all that we need to see right now is that why are two cosets of identical size. Now, the set H is a finite set, and let us say its elements are H1 up to Hm. Okay. Let the subgroup of G, its elements be H1 to Hm. Now, if you look at AH1, AH2 and AHM, these are M elements and they are all distinct, because AHI cannot be equal to AHJ for I not equal to j. This is because if you assume that AHI equals AHJ, you can multiply both sides of the equation with A inverse and you will get HI equals HJ. So, these cannot be equal, okay. And therefore, there are exactly M elements in AH, where M is the number of elements in the subgroup. Okay. So, that concludes the proof. The fact that this is a finite group was used when we said that these partitions have a fixed number of elements and each of the coset is of finite size. So, let us consider a group, and these are the cosets corresponding to H. Okay. So, let us say this is AH, BH and so on. Okay. If G were the set of integers and let H be the multiples of n. Okay. For example, if we took n as 10, then H is all those elements of the form 0 plus or minus 10 plus or minus 20 and so on. Now, these cosets are basically the equivalence classes. A is related to B if A minus B is equal to 0 mod n. Okay. Here n is 10. Okay. These cosets are precisely those equivalence classes. Okay. And we had seen earlier that we could do arithmetic, or we could add and multiply these equivalence classes themselves. So, the cosets could themselves be added and multiplied. And when can we really do this? Okay. Can we impose a group structure on the cosets? Okay. So, that is the question that we will try to answer, and in some cases we can do that when the group, the underlying subgroup has some nice properties. We can have a group structure on the cosets. Okay. That is known as the quotient group. In some sense, we are using the subgroup H to divide the group G into different parts, and then we carry out some operations, we define some group structure on the parts obtained. Okay. So, in order to look at these things more closely, we will look closely at the concept of homomorphism. Okay. We had seen the notion of isomorphism earlier, and homomorphism between G and H. So, let us say G is a group and H is another group. A function from G to H is called as a homomorphism if f of G1 G2 is equal to f of G1 times f of G2. Okay. G1 G2 is computed in G, and f G1 times f G2, that is computed in H. Okay. If this is satisfied for all G1 G2 belonging to G, then we will say that f is a homomorphism from G to H. Okay. So, suppose G is this and H is some other group, okay, and there is a map f, and it satisfies this equation 1, then we say that this is a homomorphism. Okay. Now, while we are studying homomorphism, we can restrict our attention to basically the image of f. Okay. So, let us say this is a subset to which f is mapping G to. Okay. We will restrict our attention to just those elements, the others does not really matter. Okay. So, if we call this as image under f, okay, we will just study the effect of the homomorphism by restricting our attention to just the image, the other elements do not really matter. Or in other words, we can say that we are looking at homomorphisms which are onto functions. Okay. In other words, we will just study those homomorphisms where G is mapping to the full set H. Now, this is an easy claim that you can verify. Image of a homomorphism will always be a subgroup. Okay. So, even if we had taken the larger collection and if we were just looking at the image, that will be a subgroup of H. Okay. So, that is the reason why we can restrict our attention to homomorphisms which are onto. Okay. So, let us see some properties of homomorphism. Let us see if f is a homomorphism from G to H, then f of identity will be equal to identity. Okay. It maps the identity in G to the identity in H. Okay. And the second thing is f of G inverse. So, let us say G is any element, and if you look at its inverse and look at the image of the inverse, that will be equal to f G inverse. Both of these statements are easy to verify. We will just verify the second part. Okay. So, let us look at f of G times G inverse. F, by virtue of being a homomorphism, this must be equal to f G times f G inverse, and f of G times G inverse is going to be identity. So, this is f of identity, okay, and f of identity, this is equal to identity. Now, this is E is the identity in G and E prime is the identity in H. So, what we can conclude is f G times f G inverse, this is equal to identity in H. So, this is an element of H and this is another element of H. Okay. So, and when they multiply we get identity, that means those elements are inverses of each other. So, we can write f G inverse is equal to f G the whole inverse. Okay. So, that basically is fact 2. The next concept that we will see is what is the kernel of a homomorphism. So, homomorphism is a map from one group to another which preserves the group structure, and we argued that when we have a homomorphism, the identity will map to the identity. Okay. Now, we can look at all the elements, there might be multiple elements mapping to the identity. So, all of them will be mapping to the identity. That collection is known as the kernel. Okay. So, kernel is the set of elements in G whose image is identity. Okay. So, kernel of a homomorphism is the collection of all those elements in G which maps to the identity. And this is a simple fact. Kernel is a subgroup of G. If you denoted the entire group by G, this is the kernel. Okay. So, kernel will invariably be a subgroup of G. How do we verify that? So, in order to verify that a subset of a group is a subgroup, what we need to do is verify that for every A B belonging to K, A B inverse belongs to K. If we verify this part, then we can conclude that the subset K is going to be a subgroup. Now, it is easy to check because f of A B inverse, if we can show that this is identity, then that means for every A B belonging to K, A B inverse also belongs to K. Now, f of A B inverse is nothing but f of A times f of B inverse, which is f B the whole inverse. Now, f A is identity, f because A belongs to the kernel, and f B also is identity because B belong to the kernel, and inverse of identity is identity. So, this entire thing is E bar. Okay. So, kernel is always a subgroup of G. Okay. Now, here we are in a position to state our main result, which is the connection between kernels and the quotient structure. We were asking this question, when can we define a substructure on the cosets? If we look at kernels, kernel we know is a subgroup, and we can construct cosets. With respect to a kernel K. Okay. So, let us say this is a kernel and then you consider its cosets. For this, you can multiply, I mean if you had these cosets A1k, A2k and so on, and if we define the operation on these cosets as, so let us say Aik times Ajk, okay. So Aik is the coset containing the element Ai, and Ajk is the coset containing the element Aj, and if we define this as the coset Ai Aj k, okay, that is a coset containing the element Ai Aj. Okay. Now, we can verify that this is a valid definition, because let us say Ai prime is some other element of the same coset and Aj prime is some other element of the coset Ajk. If we multiply them out, the rule says that this should be equal to Ai prime Aj prime k, but this should also be equal to Ai Aj k. So, this is what we need to verify. Okay. In order to verify this, okay, this is a set and this is another set. Okay. When are these sets identical? If you can show that one is contained inside the other, when A is contained inside B and B is contained inside A, then the sets A and B are the same. We will just verify for one direction, the other direction is automatic, the same reasoning would work. Okay. So, an arbitrary element of the LHS is Ai prime Aj prime k. Okay. Now, note that Ai prime is equal to Ai into k1 and Aj prime is Aj into k2. Okay. And therefore, Ai prime Aj prime k can be written as Ai k1 Aj k2 into k. If we could somehow show that Ai k1 is equal to k1 prime Ai, okay. So, suppose this were true, then what we can do is we can just rearrange the elements and get Ai Aj times k1 prime k2 prime k, and k being a subgroup, these things multiplies into some k3. So, we will get A1 Aj, Ai Aj and k3, okay, and that is going to be an element of the set Ai Aj k. Okay. So, what we need to show really is that Ai k1 is equal to k1 prime Ai. Okay. So, this may not be true for arbitrary subsets, but the subsets for which this is true have a special name, those are called as normal subgroups. Okay. So, we can assume the theorem to be complete assuming that Ak is equal to Ka. Okay. If Ak was equal to Ka for all A, okay, then Ai k1 is equal to k1 prime Ai. Okay. So, assuming that the kernel is a normal subgroup, we are done with the proof, because if this was a normal subgroup, then this k1 Aj, you can flip that and push the Aj to the left side and push the k1 to the right side. Okay. So, all that remains is to show that the kernel is a normal subgroup. Okay. So, how do we show this? So, in order to show that some subgroup is a normal subgroup, what we need to show is Ak is equal to Ka. So, let us say consider an arbitrary element Ak, and we need to show that Ak belongs to Ka. Okay. So, consider the element Ak A inverse. Okay. So, Ak A inverse, we claim that this belongs to K. Okay. This is because if you look at the homomorphism F, and if you consider f of Ak A inverse, this is equal to Fa times Fk times F A inverse. Now, Fk is identity because k belongs to the kernel. So, this is equal to F A times F A inverse, and this is equal to identity because F A and F A inverses and F A inverse are inverses of each other. Okay. So, A k A inverse belongs to K. Therefore, if we take A k A inverse as K prime, okay, K prime into A is equal to A k A inverse times A, which is equal to A k. Okay. So, we have written A k as a product of an element belonging to the kernel and A, where the multiplication with A is on the right side. Okay. So, the kernel of a homomorphism is a normal subgroup. Okay. So, to put things together, what we verified is that take any homomorphism, its kernel, if you consider the kernel, it is going to be a subgroup. Not just that, it is going to be a normal subgroup, and once you have a normal subgroup, the multiplication of cosets is well defined, and therefore, that induces the homomorphism induces a quotient structure or a group structure with respect to the cosets. And what we will show next is that this is the only possibility, in the sense if we can make the cosets into a multiplicative structure, if there is if this definition of multiplication is to be valid, then K must indeed be a normal subgroup. Okay. So, that is the second part. Suppose the coset multiplication is well defined, then the subgroup is a normal subgroup. So, coset multiplication we defined as if you have AH and BH, their product is defined as AB times H. Now, if this definition is to make sense, that means if it is to be well defined, then H must indeed be a normal subgroup. The way we would show this, prove this theorem, is by showing that H is the kernel of some homomorphism. Okay. So, we will construct a homomorphism for which H is the kernel. Okay. It is easy to construct. Okay. So, here we have a group and this is a subgroup, and this subgroup gives rise to various cosets. Cosets, let me call it as A1H, A2H and so on. Okay. So, now let me just consider the collection of these cosets. So, let C be the collection of cosets. So, C is a set, okay, and each element of C is a coset. Okay. And now, what we are assuming is that the coset multiplication is well defined. You can verify that the set C is a group under coset multiplication. Okay. Since the operation is well defined, we can check whether that operation is an associative operation, whether inverses are present, whether identity is present and so on. You can verify all these things and conclude that this collection C under the coset multiplication is a group. Okay. So, now let us consider our main group G and consider a function which maps elements of G to this collection C. Okay. So, an element X is mapped to the coset XH. Okay. So, clearly every element of C is the image of some particular element in G, and we can verify that this function f is a homomorphism from G to C. Okay. Why is that so? So, f of let us say x y Okay. This is equal to x y times h. Okay. By definition, f maps any element to the coset containing that particular element, and that is x y h. And since our multiplication was well defined, we know that this is nothing but x h times y h. Okay. And x h is f x and y h is f y. Okay. So, we verified that the function f is a homomorphism from G to C, and the kernel of that homomorphism is precisely H. Kernel of f is all those elements which map to the identity element of C. The identity element of C is basically H, and therefore, you can verify that every element in the coset H will map to H, and therefore, since the kernel of f is H, by our earlier theorem, H has to be a normal subgroup. So, this concludes our study of groups and subgroups and the quotient structure that is induced by a normal subgroup.